Hey guys, welcome back to chapter 11. In this video, I'm going to cover the last two intermolecular forces. This one's going to have two of them in there. So the ones we're going to cover here are hydrogen bonding and ion dipole. Hydrogen bonding. Let me again throw this out here. Even though the word bond is in this one, hydrogen bonding is still considered an intermolecular attraction, an intermolecular force. It is not an actual bond. So this is still going to be weaker than an actual sharing of electrons. So hydrogen bonding is an example of an extreme dipole-dipole interaction. So London dispersion was our weakest, then dipole-dipole. Now we're getting to hydrogen bonding. So hydrogen bonding is an extra strong dipole-dipole moment, if you will. So and it's an extreme case of dipole-dipole. Extreme case of dipole-dipole, what do I mean here? Well, there's a very large difference in the electronegativities. So these guys are going to have a very selective group that belong to hydrogen bonding. So the only guys that are going to be involved in hydrogen bonding are hydrogen, fluorine, hydrogen, nitrogen, hydrogen, oxygen. And if you were to look at the electronegativity difference between hydrogen and these three atoms, they're on the upper end of the spectrum. So remember, polar covalent was 0.4 to 2.0. And what you'll find is these guys are on the upper end, closer to this 2.0 range. So the electronegativity difference between hydrogen and fluorine, hydrogen nitrogen, hydrogen oxygen is a really large electronegativity difference. So with that large electronegativity difference, there's going to be a larger separation of charge, so partial negative, partial positive, and that's going to cause a pretty strong interaction between these molecules. In addition to the strong interaction between the molecules, hydrogen is a bit de-shielded, okay? So hydrogen has no other electrons in the nucleus. So remember, hydrogen has one electron. Nitrogen or fluorine or oxygen is hogging that electron. So this hydrogen kind of becomes exposed, if you will, de-shielded. And so it acts as a very, very strong center for that partial positive. So in addition to it being an extreme electronegativity difference, hydrogen's left out to dry a little bit, okay? It's de-shielded, it's exposed. And then lastly, if you look at all of these atoms, they're all relatively small atoms. So with these being relatively small atoms, we can approach very, very closely. So when we look at this interaction between the nitrogen of one molecule and the hydrogen of another, or the oxygen of one molecule and the hydrogen of another, the distance between those is in the intermolecular forces world, the distance between those is a very small distance because these are so small, they can get closer together. As opposed to if this were a big fat molecule, we'd have to have a little bit more distance in there. Okay. So hydrogen bonding is an extreme case of dipole-dipole because of these reasons here. Hydrogen bonding will only be found in molecules that have hydrogen fluorine, hydrogen nitrogen, hydrogen oxygen bonds. Examples we see on this paper are some of the molecules that are very important to life, and this is actually the beginning of some amino acids, or these bonds that you see happening here, okay? So you'll see hydrogen bonding in biological systems very, very often. One of the kind of interesting fun facts about hydrogen bonding is it is very important to the replication of DNA. So I'm going to take a step out of my chemistry role and into biology just for a moment. All right, so for DNA, we've got two backbones for DNA. And when we want to replicate DNA, we know that those two backbones get what we call unzipped. We replicate one side, then we zip them back up. Well, I don't know if anybody's ever explained to you what unzipping DNA looks like, but I'm about to explain that to you. So if we look at these pairs of amino acids here, what we'll see is, first off, these pairs are very particular about who they match up with. So G and C will always pair up together. A and T will always pair up together. Okay. So they're very particular. Well, why are they so particular? They're particular because of the hydrogen bonding. So what we see here is that these two amino acids line up very, very strategically, forming 1, 2, 3 hydrogen bonds between those two amino acids. Okay. If they were to pair up, let's say a G with a T, not only would those atoms not line up and match up together, but we'd also only have 2 as opposed to 3 hydrogen bonds. And same thing with the A and the T here. We've very strategically lined up 2 hydrogen bonding opportunities. Okay. So what we see here is that the 2 DNA backbones are actually held together by a series of hydrogen bonds. Why is this important? Well, hydrogen bonds are strong enough, again, intermolecular force. They're one of the stronger intermolecular forces. So hydrogen bonds are strong enough to hold these DNA molecules together. So when we want the 2 DNA backbones to be stuck together, hydrogen bonding is what does it. It's strong enough to hold it together. Maintain its strength, maintain its structure. But hydrogen bonding, being an intermolecular attraction, being an intermolecular force, is weak enough to be allowed to be unzipped. So when these 2 DNA backbones unzip, if you will, what happens is it comes through here, it pulls apart those hydrogen bonds, replicates, and then like a magnet, those hydrogen bonds come back together, they stick back together. Okay. If it were an actual bond, so if it were a covalent bond between these 2 backbones, it would just cost way, way too much energy to break those covalent bonds. That's a lot of energy that would have to go in to break a covalent bond. But because it's just an intermolecular attraction, it's just a hydrogen bond, we can get in there, break them pretty easily, and then snap them back together. Okay. So that is the next intermolecular force. The last one that we're going to talk about is the strongest of the intermolecular forces. So the last intermolecular force we're going to talk about is an ion-dipole attraction. Ion-dipole attraction is exactly what it sounds like. It's a molecule that is polar, that has a dipole moment, so a molecule that's polar, and that molecule is being attracted to an ion. Okay, so remember, ion, ionic bonding. Positive is attracted to negative. Electrons are transferred. If we've got an ion floating around and it happens to come into contact with a polar molecule, of course, positive and negative charges are still going to be attracted to one another. So this is an attraction between an ion and a polar molecule. Strength of this ion-dipole molecule is actually one of the main factors in solubility. Okay, so we know water molecules are polar molecules. We've got a partial negative up here by the oxygen, partial positive down here by the hydrogens. Okay. If the attraction between an ion, for example, an ion of sodium, if the attraction between an ion of sodium and the partial negative on oxygen is strong enough, what we'll see is that the water is strong enough to get between these sodium and chlorine molecules, bust them apart, and dissolve them in the water. If the interaction between this oxygen and whatever ion is not strong enough, then the water won't be able to sneak in between these ionic compounds. And what we'll see is it'll just fall to the bottom of the beaker as insoluble. It will not dissolve or will not break apart in solution, will not dissociate. So ion-dipole is the strongest of the intermolecular attractions, and where you will see the application most often is in solubility. So ionic compounds in water. Okay. Now that we've gone through all of our intermolecular forces, what I'm going to do is just summarize this with a couple different slides. So first we see our 4 intermolecular forces, and again, strength increases as we go down. So dispersion is the weakest, all molecules have it, then dipole, then hydrogen, then ion-dipole. And then here are just some bullet points to remind you what things need to happen in order for a molecule to display this type of intermolecular force. And then the other thing that I linked in here is a video to Tro. So this is one of those videos that you can watch. And he does a really good job of kind of animating this process and talking you through each of these intermolecular forces. So now would be a great time to stop and watch that video. So that wraps up intermolecular forces. What we're going to do with the remainder of this chapter is we're going to apply this and looking at properties. So we're going to see how intermolecular forces affects things like boiling point and surface tension, why things are gases or solids or liquids at room temperature. So we're going to apply this to different scenarios. So make sure you guys get solid on these. I hope you guys found this helpful.